Okay, so I'm AJ ONeal. I'm a software developer. I'm a DJ, like legit DJ, weddings, birthday parties, church dances, and I'm a Mormon. So coolaj6.com, that's where the blog article about BogoSort is that we're going to be taking a look at. And then there's my DJ site in case you need my DJ services. I'll even open it up for you and show you. It's very pretty. Not super pretty, but pretty enough. See, there's a picture of me in a tuxedo. I do that. I dress up for people. You can call me. I'm more of an MC and entertainer, but you know, people don't Google MC entertainer. They Google DJ. DJ is more the guy that does the wicca wicca, and I don't do the wicca wicca, but it's okay. People love me anyway. So this is something I'm working on. I'm working on a secure private home cloud, and so I'm very interested in security right now, and authorization and integration. I believe that the future of the internet, the next wave, will be the peer internet, which essentially means that we're going to go back to the 1990s when email worked for everyone the same, and we actually had this concept of like servers that could communicate to each other without knowing much about each other. And I think it's time that we bring that back because now we have always-on internet connections, and we don't need to let all of our data sit in a place where we can't ever get it back. Because who's ever gone on Facebook and you try to like search something that's old? You can't find it. Like you just, infinite scroll isn't infinite enough because you just go on and on and on. And then you have to, Twitter's even worse because you have to, it sorts feed the tweets differently based on whether you were replying to someone or not. And yeah, that's weird too. Anyway, so this is one thing I'm working on. If you want to hear more about that, you can go to dapley.com and put in your email address, and I'll be happy to take it and notify you when I've got more going with it or have some beta stuff. The other thing that I'm working on is LDS.io, LDS Connect. And what that is if you're Mormon and you have ever had a leadership calling in a stake or ward, you know how frustrating it is to use the tools that are available because the church is, it turns out, not a hot young startup, but in fact a church. And so this is an effort to provide an app store where people can, and I would love it if you back this on Kickstarter because I need some motivation to work on it and I'm running low on funds. So if I have to do contract work, then I can't do this or the other thing. So Kickstarter is awesome, but there's like 6 developers that are working on apps right now. There's only one app currently published in the App Store. But if you go down to Developer API, then you see the technical side of the site. And this is where if you log in, you'll see Playground, and then you'll be able to see like your wards and stakes you're associated with, and then all of the documentation dynamically updates with the token that you're logged in with, and you can copy and paste. And there's the examples on GitHub. All you got to do is git clone, and you can be up and running.
Does the church actually have an API for that?
They do, but it's not built in such a way that it's secure for third-party applications. So I mangle it a little bit so that I can give you the data in a secure way that doesn't violate the privacy policy. Essentially, that's your server would only get app-scoped IDs. That way, like the IDs couldn't be used. Like if your server got hacked and another server got hacked, they couldn't even correlate the IDs to be able to determine like which users fit in the Venn diagram kind of thing. There's no personal information that goes on the server. And then the client gets all the information. So it's basically the same as if they went and clicked on download CSV and then open in Excel, except that you've delivered the client through the browser and they're downloading it from me.
And you still have the ability to give individual members their own private information?
Mm-hmm.
Wow.
Yep. So that's something that it's at a base level right now. I want to expand it. So if you think that's cool, please back me on Kickstarter and share it. And then we're not going to talk about Desi today, but we're going to talk about BogoSort. So BogoSort. Is BogoSort really all that bad? Okay, so here's what you need to know. First of all, who knows what BogoSort is? A little bit? Any of you are computer science people, like you get a degree in that? How in the world could you get a degree in computer science without learning the most important sort algorithm? Come on, guys. All right. So, BogoSort is extremely effective algorithm. Effective algorithm for sorting things. So let's say you've got some numbers like 1, 2, 3, 4, right? You could run BogoSort on that list and it will effectively put those items in order. And at the heart of this extremely effective algorithm is math.random. Let me delete this. I got too big. I don't like you anymore. That wasn't good enough. Yeah, it was. Okay. Cool. And this is it right here. Now you might be confused because this says randomize, and you think, oh, that's not for sorting things, that's for unsorting things. But you're wrong, because randomize can be an effective sort algorithm, and we will see that. All right? So, but what's really surprising is that this is actually not as efficient as it could be. It's effective, but not efficient. So we'll cover that. I'm just going to copy this bit here, and if you go to my blog and you do what I did and click the is BogoSort really all that bad, then you too can experiment with this lovely bit of code. But I'll just go ahead and copy and paste it into here. I guess I could have run it in the browser, but I'm going to run it in Node because I'm cool like that, and that's how I roll. And if you don't roll that way, that's okay. There we go. All right, so now, actually, before I run this, let's talk about something else. Can I make these, is it possible to make these lights go off, just the front ones? That way we can see the screen a little better. All right, so how do you know if something is slow? I'm looking for real answers to a real problem here. Yes, sir?
The more items you try to do that algorithm over, it gets very much slower just by adding very few items to the end of it.
Yeah, but I need a definition of slow. Like, what's slow? How do we know if our algorithm is slow?
It's not as fast as you'd like it to be.
Okay, well, how do we know how fast we'd like it to be?
We usually put timer and time it before the sort and after the sort.
Okay.
So if I'm the user and I click away from the browser, it's too slow.
Yeah. Yeah. That's the answer I'm looking for. That's right on the money. Yeah, so the way we know it's too slow is if it's noticeable, because too slow means that the person that's doing the interaction has time to do multi-threaded processing, right? So they're in the thread of, I'm doing this thing, and then like that thread gets blocked, and there's enough time for them to do a context switch to another thread and continue in that thread in their brain. And they start to formulate some other thought. That's how we know if it's too slow. That's the golden answer right there. So what we need to find out is this extremely effective algorithm too inefficient? And I will submit to you that there are several cases where this algorithm is not too inefficient, because it is not, in fact, slow. So just to go over, we're going to call this sort algorithm, which is mistakenly perhaps named randomize, and then it's going to call items.sort, and it's going to pass some number between 0 and 1, right? And then the key, like the heart of BogoSort, is this function here, is in order. So the is in order function is the one that's implementation specific, because depending on what you're sorting, you're going to have to adjust this is in order to be a little bit different for your use case. But since we're just looking at numbers in this example, here's what we do: is we just say that the item that we're looking at is X, and then next is the index plus 1, right? So now where's my whiteboard? So just to make this clear, so we've got our numbers 42, 11, 37, right? So we index into 0, we get 42, and then next would be 11, would be 1, and then 37 would be 2. Those are our indexes, right? So we take our, well, if we don't have any next item, then we know that we've reached the end, so we're good there, so we can return true. And if x is greater than next, then we can also return true. So this means if we're, so this is a descending sort. So we're starting with the biggest thing and we're going to the lowest thing, right? So we're going to check to see, is 42 and 11 in order? And that, in this case, would return true because 42 is greater than 11. And then it's going to go do the next item, and then it's going to say, is 11 greater than 37? And then it's going to return false. So that is the heart of the BogoSort algorithm, a very effective algorithm. And then here, we had some suggesting of timing. Now, I submit that somewhere around the realm of 400 milliseconds is where a person has the capability in their brain to start multi-threading, right? So as long as an operation doesn't exceed around 400 milliseconds, we've got the full processing power of their thread. But if we go over that threshold of blocking for 400 milliseconds, then they start to spawn a new thread to start dealing with something else, and we lose their interest. So it is important to time it. And then here's our whole algorithm right here. So I actually use 600 milliseconds. So while the time it takes to do the BogoSort is less than 600, we're going to push an item onto our array. So we start with 42, and then we're just going to push some random number onto our array, and then we're going to call our sort function randomize. And then we're going to say, and so the sort function actually should call is in order too, right? What? Oh, I might have copied the wrong thing. Might have to copy this again. I'm going to run it and see if it magically works somehow, but I don't see where in it is in order is called. Oh, I bet it's time BogoSort. Okay, yeah, so we call, that's where it actually happened. We were actually doing the BogoSort right here. Okay. So any questions on what's going to happen with this algorithm? Can anybody explain in simple, non-obfuscated terms what this actually does?
Sort numbers?
It just randomly rearranges them until they're in the right order.
Yes, that's BogoSort. Okay, so here we go. Boom. So check this out. If we want to sort one item, 0 milliseconds, 2 items, 0 milliseconds, 3 items, 0 milliseconds, 4 items, 0 milliseconds, 5 items, 0 milliseconds, right? So we get all the way up to 8 items, and a person can blink, and that sort is done. So that is efficient enough, right? And then here, 9 items. That's where it starts to get slow. So let's run it just a couple more times just to see, because it is random and all. So maybe that's just an outlier. 9 is getting pretty close. So 10 sometimes gets in there, but then sometimes 10 is really, really far out. Okay, so now we've got a benchmark for our BogoSort. Now, I don't know about you, but occasionally, very rarely, I have a list of items that is longer than 9 items long. That's mostly because I have 10 fingers, right? I can count to 10, so usually once I get to 10, I just stop. So the only problem with this algorithm as I see it is that we need to be able to handle at least 10 items. Fortunately, there's a way to do that. So we're going to make BogoSort faster. And then we'll talk about that. All right, so here was my actual results when I was running this test multiple times in a row. And we will get onto actually useful information as well. I promise. It's not all just goofy nonsense. Okay, here we go. No, that's not what I wanted. Give me my good BogoSort. Okay, I'm going to have to just copy and paste. Not surprised. Oh, optimize BogoSort. There we go. All right. So it turns out that math.random actually isn't random enough. And that is one of the factors that makes our BogoSort slower than what it could be. If we had a better random algorithm, we would actually get faster results. So contrary to what you think, we actually increase the number of operations that we perform by quite a bit. So this randomized function here is, it's got quite a few more operations in it than just calling math.random. In fact, we end up calling math.random in a big loop, right? So this algorithm for randomize is we take every single item, all 10 of our items, and we run this math.random function on every single one of them. So instead of calling math.random once, we're calling it now n times, however many is in the loop. So you'd think intuitively like, oh, well, this algorithm is going to run a little bit slower because I'm actually doing more work. There's 10 lines of code here instead of 1 line of code here. So I'm just going to take my randomize function, and then I'm going to copy and paste it back into my BogoSort. And I'll get rid of the old one, or maybe I'll just comment it out, actually. That seems like an all right thing to do. All right, now we run it again. Look at that. Get up to 10 items before it starts getting slow. And this is consistent. I mean, like there are outliers. Here's an outlier. But it's fairly consistent. Dang, there's a lot of outliers this time. There we go. Got 10 that time. The problem is that when you get to 11, it sometimes takes like 30 seconds, so I won't actually let it do that. But I ran this over and over and over again, and I got the averages, and I found that by changing the math.random, we actually get a more efficient BogoSort. Okay, yeah, so if we look, here's some averages I did. So list size in milliseconds, list size milliseconds, and then this one was actually using the higher resolution timer because I wanted to see, 0 milliseconds. The difference between 0 and 1 is just as great as the difference between 1 and like 100 million. Because at 0, you're not able to quantify anything, so you don't know what goes on between 0 and 1. So if you use Node's HR timer, you can actually get finer resolution so you can see like how small of a 0 or how big of a 0 was that 0 milliseconds, and you can see.
1 and 2 take longer than 3?
That's a really good question. It probably has to do with optimization of the VM or something like that. And it's random.
So by the time you get to 3, something's been just in time compiled or something?
That might be it. I don't know. But yeah, I mean, you'll notice fluctuations like that when you run the code. Or it could.
I'll bet that's what it is, actually. I'll bet that, because that engine, you can correct me if I'm wrong, but that engine, when you're looping over things, the engine V8 compiles stuff down to raw C.
Yep. Well, it's assembly.
Yeah.
Yep. Yeah. Okay, so why is this important? Because this seems pretty senseless. Well, it's important for 2 reasons. One, it's important legally. It's just important to know that that math.random is a poor legal choice because, let's see, do they have the picture here? They've got all the graphs. Where's the picture of the website? Let me... Let's see if this loads. Nope. Okay, so Microsoft had a website called Browser Choice. And it was because in the EU it's illegal for them to monopolize the browser market. So when you went to open up Internet Explorer, the first page that it had to bring you to before it let you do anything else was, which browser do you want to use? And so it would have Chrome, Firefox, Safari, whatever the common browsers are, Opera, right? Like 3, 4, 5 browsers, whatever. But the problem was, they got sued for this, that Internet Explorer always tended to be the one that was the most right when it got sorted. And that's because math.random is broken. So that's something important to get out of this is that math.random is broken, and that the Fisher-Yates shuffle or Knuth shuffle, which is like way cool, and I'll show you the link to that, is definitely a better math.random if you need to use math.random. But there's a more important lesson here once I show you that. This is just kind of cool. Let me go. Okay, here's the visualization. I think the good one is all the way at the bottom. So this is how Fisher-Yates shuffle works. That's what I replaced my random with. It does this. It takes your whole deck of cards and it sorts the entire deck by randomizing each index and then swapping it with some previous index that hasn't yet been randomized. So it starts with like, I'm generating a random number between 0 and index, and then 0 and index minus 1, and then 0 and index minus 2, and so on and so forth. And then it swaps whichever number it gets with the index that it's currently on. And so that's how the Fisher-Yates shuffle works. And it's a good random function. But the more important part of what this story is I just described to you most of your time. You spend so much of your time optimizing the stuff that doesn't matter and ignoring the stuff that does. You spend so much of your time thinking about like these nitty-gritty little details that don't matter, like this math.randomize function, and you ignore the big picture of, hey, I'm using BogoSort, right?
Plus in front of or behind the...
Exactly, right? Like we as developers, we're terrible about like making the right conscious decision because it's fun, right? It's like a crossword puzzle, or it's like a desk puzzle, or it's a game to us. Like we get caught in this like, oh, there's this one little component that I happen to be working on right now, and regardless of how it actually affects the application, I just want to spend my time on this. And I'm not saying that that's like bad in terms of an intrinsic quality, because hey, it's rewarding. Like it's cool to be like, yeah, I developed the most efficient randomized function. Our randomized times went from I got a 100% increase on the amount of CPU efficiency I was able to do with that. And I feel good about it. But then when we're using language like JavaScript and you're going over like, oh, well, maybe if I put the plus first, like it's JavaScript. It doesn't even care. Like it doesn't even get compiled that way. It doesn't know. It goes through a bunch of like jitting and all this mess, and then it goes down to assembly anyway. It doesn't matter whether you do I++ or ++I, that kind of thing. But so, I mean, like the real goal is we want our applications to be fast enough that a user can use them. And in some cases, this is another point, is BogoSort is actually okay. Like if like you're like, hey, I need to get these things in order real quick. And I remember AJ's talk on BogoSort, right? And you just go to my blog and you copy and paste this code, and the things that you're trying to sort are no more than 10 items long. Well, maybe closer to 8. 8 seems a more safe bet, right? But as long as the number of items that you need to sort are in that way, if this is the quickest way to be productive, you're like, I need to copy and paste a sort algorithm. AJ's got a sort algorithm. You go to my blog, you copy and paste it, and you use it, and the user experience is that they blink and it happened, then you're good. Like you don't have to optimize beyond that. At least not on the client side. On the server, you might want to be a little bit better. So we don't have to spend all of our time worrying about these nitty-gritty details and performance tests, because a lot of times what we're testing is the wrong thing. We got to think of like the user blinks. When I'm blinking, if I blink twice, that was enough time for me to start thinking about something else. Okay? So that's what we need to focus on. However, I did also promise a sneak peek of Algorithms the Musical, so I have a little opera number that I'll sing for you now. Big O-N, big O-N, big O-N squared, in login. Big O-N, big O-N, big O-N squared, in login. And that's all I comprised for that little mini opera. But big O is something else that we need to talk about, because sometimes what you're doing is important, and a lot of times it's a really simple fix to make it faster. It's just the order that you do things. So who is familiar with Big O? I know there's some CS people in here. So you guys are all familiar with Big O, right? Somebody give an explanation of what big O means to the other peoples.
Simple or hard explanation?
Well, we want to go with simple.
It's a quick description of the time it'll take to do an operation as the set grows.
Yes. I like that. All right, so big O is in. So I'll write it down because it makes a lot of sense when you write it down. Big O means order. So order is like exponent. So like in to the 0 is always 1. In to the 1 is always in. In to the squared is bad. And then like the absolutely worst possible thing you can do is BogoSort, which is in factorial, which means n times n minus.
All numbers less than n down to 1.
Yeah, so if it's like 5, then it's 5 times 4 times 3 times 2 times 1, right?
Right, so with your last sort, for example, when there are 9 items, there's 362,000 possible sortings, right? That's why it takes. When you get to 10, it's logarithmic.
Yeah, exactly.
When you get to 10, it's like 3 million, and 11 is like 30 million, right? It grows very quickly, and that's why anything over 10 is ridiculous to BogoSort.
Yeah, exactly. Exactly. So big O means the order that we're dealing with. Are we dealing with like, and then the notation is you basically just put in one of these type of things. And so the common things that you'll see is there's in. Well, the best one is 1. That's what we call God sort. So God sort is, since God is an all-powerful being, if you believe in God, I do, but he's an all-powerful being. So if he had some sort of list of items and he wanted it to be sorted, he'd just be like, order 1, bam, it's sorted. Be sorted, it's done, right? So this is the God sort, or the God algorithm, right? And in some cases you can get there, but usually you can't. And then there's O(n), and then there's like O(n) squared, and then there's O. In log n is usually like what we're trying to get to. In log n is like the happy medium. And I meant to bring a phone book, but I forgot to bring one. Does anybody have a book on them? Okay. Magazine works. Yeah. So I'll try to explain this a little bit. Object lesson here. Okay, so I've got this magazine. This is what we normally can get to as a best case. Is I've got this magazine and I want to find something in here. So this, I don't know if this is, well, this is sorted by page number, right? So somebody shout out a page number that you think would be in here. 23? Okay, so I open it up to about the middle. Oh, look, that was perfectly the middle. And I check to see what number it is. It doesn't have numbers. Okay. All right, so the number that I'm on is 28. And so then I decide, okay, 28, is that greater than or less than? And oftentimes we're dealing with sets that aren't perfectly sequential, like 42, 11, 37, not like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all I know is that 23 is likely to be in this half. So I open up this halfway, and then I see what number I'm on. That was a little less than halfway, and this page doesn't have a number. All right, now I'm on 13. So I know that 23 is going to be greater. So I take it and I open it up halfway again. I mean, this is the intuitive sort. This is like human sort. This is how you sorted a phone book as a kid, right? You take a guess, and then you just halvesies till you get there. Right. So now I'm on 17, and then I have it again, and now I'm on 21, and then I have it again, and now I'm on 23, right? So I was able to get to this in an in-log-in algorithm, which means that basically whatever number the exponent is, more or less, it's like whatever number the exponent is, that's the number of things that I'm going to have to do before I can find it. So that's called binary search, is the most well-known in-log-in algorithm. You guys heard of binary search? Okay, well, if you hadn't heard of binary search, you have now, and it's exactly what I did. And that's how you implement it in code, is you have some sort of list that has a sorting that already works to some degree. And then this is how databases work, right? Like you've got 1 million records and you want to find ID 27, and it's not going to start at 0 and go 1, 2, 3, 4, 5, 6, 7, 12, 15. it's going to go halvesies and and this is how trees are sorted. They start at one element and they check the element on the right and left and they go down. So if you ever have to do that, it's really fun to implement, I think. But that's like normally the best case that we're trying to go for. And then order one is like a hash or an index. So like if you have an array and you go to index 1, in JavaScript this is actually a hash, but in C it would be an index, but they're pretty equivalent because when you're talking about, like if I have to do 3 operations, that's still considered order 1 because the order of magnitude is in the ones, meaning there's not multiples. But if I have to do some unknown number, then that's considered in. So even if it's only one operation, it's still considered in because it could be 10,000 operations. And then if it's order 2, that means that if I have 10 items, that it could be 100. Or if I have 1,000, then it could be 1,000,000 operations. So that's an adequate description of, I lost my place. Okay, so you index in, right? So indexing in is if I know an index, like a number, then in memory, in the computer's memory, I can say, take the size of this thing. Like I'm dealing with, say, integers. I know that they're 1 byte long. So I'm going to multiply the number of bytes, and that's going to give me the memory address. If I'm using a dynamic language like Ruby or JavaScript, what it actually does is either, we don't talk about array lists because those are inefficient, but they're done with binary trees a lot of times, so they're efficient enough. But the other way is the hash, which is where you take something like the string, a person's name, say Bob is the ID we want to use, or like a big long UUID. We calculate how many items are, say, in our database. And we multiply that usually by 2, or depending on what our growth rate we expect to be, but let's say 2. So let's say that I have a contacts list on my phone. The phone can assume that I'm going to start out with, say, 5 contacts, right? And so it can allocate 10 spaces, and it'll just perform a hash. Like, has everybody done MD5 sum? Okay, so it's almost the exact same thing as an MD5 sum, except a lot faster and not meant to be cryptographically secure at all. It's just meant to be fast. So you have some sort of sum that will narrow the thing down between a set of numbers. And then it just indexes into that bucket. So Robert actually turns into the number 4, and then it goes into bucket 4 and then finds Robert. And then if the list is really long, like as it doubles, then it will, so let's say like we have a collision, like we put in some other person's name, John, and then his name somehow hashes to 4 also, then the list automatically doubles, and then from it reassigns all the numbers and it generates a new hash algorithm that's slightly different, and then that's how it can index in. I probably totally mangled that explanation. Was that clear at all? Okay. All right. So that's the indexing thing. And so when we have, the contact list is a really good example. When we have something like a contact list that has 10,000 items in it, like, I mean, I don't know about your phone, but over the years, like every single person that's ever emailed me somehow gets into my contact list. Like every single phone call I've ever made seems like, it through all the different tools that just kind of automatically add things, my contact list is probably around 10,000. And that is like 10,000 I kind of observe as like the magic number where slow happens. Because you can take anything in JavaScript or Ruby or like whatever language you want, and it seems like until you get to 10,000, it doesn't matter what operation you're doing. Like at 999 or 9,999, things are fast. But the moment you hit 10,000, it's like all of a sudden things get slow. Has anybody else had that experience? Or feel like that's kind of around that range?
Magic numbers, but I don't remember 10,000. I don't have that in front of me.
Yeah, I guess so. When I use the Firefox phone, its contact list is actually implemented a little bit poorly. So when I did my import from Facebook and Google accounts and all that, like when I go to search for a person, and you might remember this from when Gmail initially released their app on iOS or on Android, where like you could type and it would like wait before you could type the next letter because it was performing a terrible search algorithm on your whole list. So when things get slow, that's when you want to optimize. That's when you want to figure out how to try to get an in-log in or a binary search type algorithm implemented.
So maybe even more importantly, the counter example is don't optimize. Don't waste time optimizing until you get to the point where it's slow enough to cause pain. Don't optimize before you have to.
Right.
Don't want to optimize the wrong things, waste of time.
Yeah. And so that goes back to our the original example of we were spending all this time talking about BogoSort and then trying to make BogoSort faster by improving the random function that it uses. That's the exact same thing. Like, we didn't need to optimize the randomize function because the randomize function, although, honestly, you shouldn't use math.random, that wasn't our real problem. That was just a sidetrack. And we didn't experience our real problem until we got to that size. So, yeah, that was kind of one of the major points that I was trying to hit in this, is don't try to optimize things unless you're doing it just for fun. If you're doing it for personal entertainment because you're like, oh man, I've had a hard week and I just need something a little mind-numbing to relax me, and you want to implement something and make it faster for no good reason, by all means do that. But don't try to optimize when you don't know that there's actually a problem. The epitome of that in my life, this is the last thing I'll share, I think, was I once was concerned that I might have a list that might get to around 50,000 items, and that's not what I want to be at. Where is my, click on me? No, click on me here. Click on this, yeah. What was it called? Circ. Wait, where did it go? GitHub's been buggy lately. So I created circ.js, which is a circular buffer. So the idea is that sometimes you want a set of 50 items, but once you get to 51, you just want to overwrite the first. It's the same thing that the Chinese do with any of the memory cards that they sell you. Like, they say it's 1 gigabyte because it can just keep on writing, and then it'll just overwrite the first 5 megabytes over and over again. Anybody ever bought one of those? I have. So that's what the circular buffer is. And because JavaScript, when you add something to the beginning of an array, it actually has to resort the entire array in order to be able to do that. And so I was concerned that when this got larger, the thing I was working on got larger, that that would become slow because every single push means that for all 10,000 items, it has to resort them. And then when I actually ran tests on it to figure out whether or not it was faster or slower, it was actually slower up until about 100,000 items, which I was never going to get to. So I spent all this time on this thing that turned out to be fun, but wasn't actually useful. It was detrimental to the problem that I actually had. And then there was one other thing. Just a challenge for if you are ever in the mood for solving a challenge because you're just kind of wanting to relax. Does anybody write code to relax? You pick some problem, just, little small problem, and this is going to take me an hour. This will kind of help me calm myself. If you Google CoolAJ6 and Hot Plate, there's other implementations of this homework assignment. But this is a homework assignment for college students and people at code camps and whatnot. And the point of it is, and this is not algorithmically challenging, this is logically challenging. The point of it is you start out with a grid that is 0 in the corners and then 100 in the center, and this represents a temperature, like a burner, and then 50 everywhere else, and then every single turn, everything gets the heat of what's adjacent to it except for the corners in the center. They always stay the same heat. The corners are always ice cold, the hot's always red, or the center's always red hot, and you try to calculate the number of turns it will take until the values stabilize. So here's the first turn, that's what you start with, and then the second turn would look like this, and then when you end, you get numbers that look like this depending on if you're calculating to the hundredths or the thousandths or the millionths or the 10 millionths place. And so this has kind of the instructions on how to do that, or it had a link to the instructions or something. Or, no, I think I don't have lots of instructions because that's all you need to know is what's there. Yeah, anyway. So if you're ever in that position, this is kind of unrelated, but this is kind of a fun problem to solve. And if you're a good computer scientist, then you can solve this problem. And if you can't solve this problem, I would encourage you to become a better computer scientist. Because when you can solve problems like this in your free time because it's relaxing, you're in a good place. You're also probably in a place where you're optimizing the randomized function for no reason, but hopefully you don't do that too often. So I know that was a little scattered, sorry, but I hope that it was a little bit fun, a little bit educational, a little bit entertaining, and thank you.